So in this lecture, we will be continuing our discussion on memory management, the memory management of the operating system. So in the last class, we covered some portion of this topic, and we shall continue today with the other concepts. So let me quickly summarize what we have covered in the last class. We try to understand the basic role of OS in handling the memory. Why do we need memory management, and what are the how it has evolved to handle memory in a more better and efficient way. So if you go back to the history of design of computers, it all started off with the bare machine model, where bare machine in a sense that there's only one program which is there in the memory, only one program, and the CPU reads all the instructions one by one and executes them. Because there is only one program running in the memory, there is no need for any kind of operating system in this case. This is usually the model that is used in low-end devices, the embedded devices, the different electronic gadgets that you find, etc. So this is the model that is used. You have only one memory which holds or which can hold only one program, and the CPU executes them by reading the instructions one by one. Obviously, there is not much of a complexity, so you don't need any kind of operating system, etc. But if you would like to improve the efficiency of this system, you have to introduce the concept of multiprocessing, which means you want to run two processes at the same time. Why? Because if one process goes into a blocked state, which happens for every process when it goes into an IO access mode, it gets blocked. And to utilize that block time, we allow another process to run. And we have been seeing this, how multi-processes can be executed on the CPU through an interleaved way. So this is the idea where we want to have multiple processes, more than one process we would like to execute on the CPU. But the moment you improve or you increase the complexity of your system, that is, you allow two processes, they have to be managed efficiently. So they have to be allowed to get executed in a timed interleaved way. So everything is handled by another piece of software or a process called the OS. So now the memory has three processes: the OS process, process P1, and process P2. Process P1 and P2 are user-defined processes, and the OS process, or we usually call that the kernel, is responsible for handling the operation of the other two processes. This is how memory starts holding more than one process. Okay. Now, when we begin multi-programming, we saw that multi-programming involves movement of processes from the CPU to the memory, from the memory to the CPU in this way. Now, there is a situation where one process may request or may get blocked, and we need to allow some more processes into the memory. So the situation that we saw was that there were currently two processes, P1 and P2, and this P1 and P2 are sufficiently large processes that are occupying enough space in the memory, so there is no space for another process, P3. So how can we ensure that this process is also accommodated in the memory? That was the problem. So the solution was that you find out among the processes which are running, P1 and P2, which is taking more time. If you find that P1 or P2, one of them is taking more time, or is it basically put in the ready queue for long, you can move that out into the hard disk, and the P3 which is residing in this can be brought here if there is sufficient space. So this is the concept that people thought, that if one of the process is remaining idle for long, you can put it into a suspended wait state and push that back to the hard disk, and one of the process from the hard disk can be taken out. This is what the idea was. Now, to fasten this to make this swap out and swap in process faster, this is called swap out and this is called swap in. To make this faster, people thought, okay, why not we introduce a buffer in between the two. So if this is P1 and P2, let's introduce two more spaces. Okay, the two buffer spaces, buffer 1 and buffer 2. And what could happen is, now this swap in and swap out usually happens in sequential way. First, a process is swapped out, P2 is sent back, then P3 is brought in. Now this can be time consuming. So can I overlap this? So it can be in this way that, okay, the process P2 is moved to buffer 2 and from buffer 2 it is going to go into this, whereas the process P3 would come here in buffer 1 and next time it will go back into this space. So this is how the processes would move in the memory. And this process, the swap out process, okay, the swap out process and the swap in process can happen simultaneously because they are happening at two different locations of the memory. So they can happen parallelly and that saves a lot of time. So this gave us an idea called the multi-programming with fixed partition. So you have the fixed partition. And so what the idea came up is that, okay, if you have a memory and you want to hold many processes into that, you divide this into number of blocks, and more the number of blocks you divide, the better. Okay, so you keep on dividing this into a number of blocks, and for each block would be allowed one particular process. Okay, and in addition to that, you have the OS. So this is the concept that came up. And the number of processes that are currently held in a memory is called the degree of multiprogramming. But fixing up the partition led to a problem. That is, the block sizes were fixed, but when the process was put into this particular block or was allowed into this block, there can be a situation where the process would not occupy the entire allocated space. The process requires lesser amount of memory than the one that is allocated to that. And that is what we call fragmentation. Fragmentation was of two types, internal fragmentation and external fragmentation. Internal fragmentation was when a process could not occupy the entire space and some space remain unoccupied. And if this happens for many processes, so the entire wasted space, if you sum them up, you find that that is enough to hold one more process. But these wasted spaces are not at one place, so one more process could not be accommodated. This is the problem which we call external fragmentation. This was solved by introducing something called segmentation and paging. So these were very interesting ideas where people thought that, okay, what we will do is we will try to introduce the concept of virtual memory, and where instead of the entire process at one place in the physical memory, we divide that into its chunks. Say, for example, there are three processes shown as blue, red, and yellow. Instead of the entire entire process at one place, we divide it into three blocks, and these three blocks are distributed all throughout the physical memory, as you see here. The entire range of addresses of this red process shown in red is distributed into three blocks, and it is in three different places in the physical memory. Similarly, three different places of the blue process, the yellow process. This is a very interesting concept, and that eventually allowed the processes to be distributed in the physical memory. But this is not how the CPU or the user looks at the process. The user or the CPU looks at a process as a set of contiguous memory locations, one stretch of memory location. It doesn't understand distributed nature. So to give a unified view of the entire process space, CPU we came up with a concept of virtual memory, which is one single address space, and the CPU would generate addresses for that particular logical or virtual memory, and that eventually would get translated by the memory management unit into the corresponding chunk in the physical memory. So this was how the two address spaces were related. The address generated by the CPU was a logical address or virtual address, and the address that actually got mapped to was the physical address. This is how, or this was the requirement of, removal. This was required because we wanted to remove the problem of fragmentation. Now this memory, this translation can happen in two different ways. One is called segmentation, where the entire address space was divided into different blocks of variable size. And these blocks were decided based on the kind of information that was required or that was put in that particular block. So if you look at the entire address range generated by the compiler after compilation of a program, so address space of a process, we see that that consists of the stack portion, heap, data, and code. So you can treat all these four different kind of information into four different segments. So the entire address space, this block that has been shown here, is the address space of a particular process. So that can be thought of as divided into four segments: the yellow, the light blue, the blue, and the green, and each one of them is consisting of some kind of functionality of that particular, either the stack portion, the heap, data, or the code. So this is the virtual address view of a particular process. Now, this has to be mapped to, say, for example, this entire thing physically. If this is the physical memory, let's say this may be the stack, this may be the heap, this may be the data, this may be the code. It can be absolutely randomly placed in the physical memory. This is the physical memory. So they have to be mapped. This fellow has to be mapped to here. This has to be mapped to here. This has to be mapped to here. So this mapping has to be done. Somebody should take care of that. And that is what is done by the segmentation part, the segmentation unit. So what the idea was that you maintain a table, and the address that will be generated by the CPU will be a logical address. That address would take you to one of the locations of the table. And what you have in the table is the base of the segment and the limit. Limit means what is the extent of that particular segment. So if this is the memory and if this is the segment, so this is the base address, and the entire range of addresses that are held in this block or in this segment is the limit. So this table contains such base address limit pairs, base and limit pairs. And this is segment number 0, segment number 1, segment number 2 in this. So for every segment, we keep a base limit pair. So the logical address is split up into the segment number and the offset. Offset is, suppose the address is generated for a particular location of the physical memory, but that location which the CPU wants is part of a segment. So you first locate the segment for which the address is a part, and then you find out how much of it is from the top of the segment, that is from the base address of the segment. That is called the offset. So what we do in case of a segmented scheme, the address which is generated, the base address is identified. Base address means you reach to the segment. Then you see whether the address is going beyond the limit. If it is going beyond the limit, then you are having an unauthorized access. But if it is within the limit, then you add the offset to the base address, and that takes you to the address that is actually required, and that is called the linear address. This is the concept of segmentation. We saw different segmentation of the Xv6 operating system, and we also saw some advantages and disadvantages of this particular scheme. The advantage was that you can very easily handle this minimum amount of information required in a segment table, but it still could not remove entirely the problem of fragmentation. Then there was another improvement to this segmentation, or you can say another way of implementing this, where we fix the size of those segments. And once the size of that particular segment gets fixed, we call them as pages. So this scheme is called the paging scheme, where the idea is that in case of the virtual address space is divided into fixed number of blocks called pages, and similarly physical memory is also divided into fixed number of blocks called frames, and page size is equal to frame size. This is the condition that is imposed. So all the pages or any page exactly fits into one frame. So this is the virtual address and this is the physical memory. So to map a page to its corresponding frame, the paging system uses a table which we call the page map table. So for every process, there will be a page map table. The number of entries of this table would be the number of pages that has been created. So if this is 1, 2, 3, 4, 5, 6 pages, there will be 6 entries in the page map table. Each entry corresponds to one page. And what is inside this particular each entry? So what each entry of a page table contains is the equivalent frame number. So page number 0, let's say, corresponds to frame number 1, 2, 3, 4. So it should contain, this is frame number 0, 1, 2, 3. So page number 0 corresponds to frame number 3. This is what is the idea of paging. And when an address gets generated, the CPU generates a logical address. This logical address is split up into two parts. One is called the virtual page map, or the virtual page number. So this virtual page number gives you the index of the page table. And once you reach to that particular page entry, page table entry, you read the contents of that and you get the frame number. Once you get the frame number, add that value to the rest of the bits of the logical address, which is called the offset. What is offset? Well, offset is if this is the page and the address is actually required for this particular location. So this is the offset. Because one page fits exactly in the frame, so the offset in case of a page would be the same as offset in case of a frame. So that is the reason why we just obtain the frame and add the offset to that, and that takes you to the equivalent address in the physical memory as well. This is the concept of page translation, and we had seen till this. We saw an example. Well, now in addition to the frame number which is contained in a page, there is something more in a page which we call the protection bits. So what is this protection bits? As you see here, protection bits is something which is required. What are these protection bits? What do they contain? They contain these 4 kind of bits. Each bit has a meaning. By the way, these are also entries of each page table. Protection bits are also contained in each page table, each entry of a page table. What do they have? Protection bits, some of them is called a present bit. What is this present bit? It is a map to a valid physical page. It is a mapping to a valid physical page. Okay, I'll show you with an example. So let's look at this. Yeah. So suppose this is page 0. You have generated an address for, let's say, this particular page 2, which actually doesn't exist. Okay. So, but this entry will be there. The page 0, page 1, page 3. You have obtained 3 pages of the virtual memory. And when you maintain that, in case of when you maintain this information in a page table, you see that the page table will have 4 entries, 0, 1, 2, 3. But this particular entry, the entry of this particular page table, which is page table entry 2, it doesn't have any valid page in them. So how do you show that? How do you, inform that there is no valid page corresponding to this particular entry of the table? That is done through these bits. So as you see, it is nothing but a representation that there is no valid page corresponding to this particular virtual page address. Okay, this is the meaning. In addition to that, you have a read, write, and execute bit, which tells me that what you want to do on that particular page. Do you only want to have a read information or a read permission, a write permission, an execute permission? What kind of permission you want to give? Then you have the user bit. Who can access it in the user mode? Is the user allowed to access it in the user mode? So these are the 3 bits that tell or that contain some additional information apart from the frame number. Say, for example, I've written it here as 000. What does it mean? It means that this is not a valid page, and there is no meaning of the read access or whatever. So the read access or the user bit, there is no meaning, because it's this bit itself will tell that it is an invalid page. So no need to go further. And obviously, so if it is an invalid page, so page number 2 doesn't have any page corresponding to it in the physical memory, as you see here. So it's the additional information. Okay. Now comes the page allocation. So we understand that paging is a method of managing the memory and how efficiently memory gets managed. Now the concept is how the pages are allocated. The page allocation is done, or we can say free page management. What are the 3 things that we are going to, or rather the 2 things that we are going to. Okay, so there's a request to repeat this page protection. Let me go back to this example. As you see in this example, every page has its equivalent frame number. So every page has its equivalent, has an entry in the page table. And what do you have in the page table? The equivalent frame number. There are 4 pages of this virtual address space. These 4 pages lie in this way in the physical memory. So this is frame number 0, 1, 2, 3, 4, 5, 6, and 7. Page number 0 corresponds to frame number 1. So what we have in this case is the frame number. Now, suppose page number 2, there was no page number 2. Okay, there is no page number 2. Just page number 0, page number 1, and page number 3. So there is no entry for this. There is no entry for this. So number of pages is 3. Let us assume number of pages is 3. But the page table entries will be, number of page table entries will still be 4. Because page table will have to take 0, 1, 2, 3. Now what will you put in page table number entry 2? What will you put there? You will not put anything. There is no frame corresponding to this. But how will you inform that to the kernel that there is no valid page table? For that, we have made use of some additional bits. So these additional bits that you see here, this bit, for example, is an indication that, let me call it as an invalid bit. It is an indication there is no equivalent valid page. I have written a frame number here. I've written a frame number, but that is not a valid page. Okay, because there is no equivalent frame corresponding to this particular page. There is no page. So there is no equivalent page corresponding to this frame. How do you tell that? Well, you tell it through this particular bit. This is one. Let's take an example of this. Page number 0. Page number 0 corresponds to entry number 0 of the page map table. entry number 0 of the page map table. And page map table entry number 0 contains a frame number 1. So this will take you to frame number 1, the base address of this. Okay, good. But when I have reached to that particular page, I should know what kind of permission is provided or given to me. This will be told. So it's 1, which denotes that it's a valid page. Valid page means a page exists in the physical memory. In this case, this 0 denoted that there is no physical page corresponding to this particular virtual address. This is a valid page. What is this? This will be a permission to tell you whether you are allowed to write, execute, or only read. What kind of a permission has been allowed for this particular page? Okay, this bit will tell you. Let's say I decide that I'll have, or maybe both these bits will decide. Because with 2, I can have 4 different combinations. 0, 0 will be your, let's say, read. 0, 1 will be write. 1, 0 will be execute. So I can decide what to do with this. This is what I mean by protection bits. They are additional information along with the frame number. Is it okay? Okay.
Sir, how there isn't any virtual space for the page 2?
How can?
Sir, how is it possible that in the virtual space, page 2 is not there?
We'll see. I'll show you when it is demand paging. Maybe it has been replaced by someone. The page has got replaced.
Okay, sir.
Okay. Let me show you this. So now the question is, okay, now that we know that pages are there and pages have to be, we work with pages, how are they allocated? How does the kernel allocate the pages? So what kernel does is it maintains a list. It maintains a list of all the free pages that is there in the system. Free pages means from here. So as you see, whenever there is a particular, a process has to be allocated some space in the physical memory, equivalently its page table has to be updated because the page table is the one that maintains the mapping. So whenever a new process is created, its page table gets created. And whenever that new process is allocated some space in the physical memory, the first thing to do is you just update its page table. Okay, so the page table gets updated. Now, how is this, when a new process comes, how do you allocate those pages to a particular process? So what happens is the kernel, it maintains a list of these pages. As you see here, this is a list of these pages and it is called a free page list. Okay, it's a free page list. So as you see, this is the pointer to this particular page. And from here, there's a pointer to the next one. Then look at this. Page number 0 is occupied. Okay, so page number 0 is occupied. Page number 1 is occupied. Page number 3 is occupied. So the green ones are occupied. Who are left? The blue ones are left. So these are the pages or equivalently frames. So these are the frames which are free. So when a new process comes, let's say page 0, page 1, page 3 are the pages of a particular process called A. Now when a new process is created, process called B, this will also require some frames or pages to be allocated. Now which pages will be allocated? How will the system decide? So look at this. This is the pointer, which is the head. This is pointing to the next free location, which in turn is pointing to the next free location. This is pointing to this free location, and this is pointing to this free location. So it's a list that is maintained of the address ranges. This is the free page list. So whenever a new page has to be allocated, one of the page is obtained from this free list, and then you can allocate it to a particular process. Okay, this is how things happen. So the system maintains a free page list and it picks up one of those free page addresses, the addresses which are kept for allocation of pages which are free, and allocates it to a particular page. Now, what is the algorithm for allocation? What is the policy? Policy is one page will be allocated at a time from head of the free list. Obviously, it's a linked list. It's a list. So the current head will be the one which is the candidate for allocation. The moment this will be allocated, the head will now shift to this particular location. So if X is a list which is pointing to page number, the address, if the base address of this is pointing to base address of this, when this is getting occupied, so this pointer is, the head is simply, or maybe let's put it in this way. Suppose the head is currently X and X is pointing to Y. So after X is allocated, head will be updated by Y. That's what it is. So this is the way the allocation is done. So as you see, this is the list that is maintained. The list is page or frame number of this is what, 0, 1, 2, 3, 4, 5, 6, 7. So what is the free list? The page, the head is currently 0, 1, 2. This is the head. This is pointing to 3, 3 is pointing to 6, 6 is pointing to 5, and 5 is pointing to 6. That's the list that is created. Okay. This information is in Xv6 present in a file called kalloc.c, calloc.c. Implementation of a page table. This is important. As you know, page table is the data structure that is the most important data structure that contains every information about the page map. Where do we store page tables? Page table is a data structure, it's a table. So where do we store this table? Where do we store? We store it in the physical memory. We don't have any other space. So the page table is also stored in the physical memory. So see, here is the virtual address space, right? This is the virtual address space of, say, process P. This is the page table. And this is the physical memory, which contains these chunks. Okay, these. But in addition to that, this table, which is the page map table, is also present in the physical memory itself. This is also present in the physical memory, let's say. Okay, so this page table, where do you hold that? Well, you hold it here. Okay, so you hold it here. So page table is stored in the memory itself. Okay, page table is also stored in the memory. How do you access a page table? Because you know that every address that you generate, CPU, that is actually accessed through a page table. And page table is remaining in this. So how will you decide that which portion of the memory is a page table and which portion contains the processes? How do you do that? Are you able to understand the problem? I said that every process is located through its page table, but the page table is also in the physical memory. There is no other place where I can keep. It is also in the physical memory. So first of all, tell me how many memory accesses do you require to access a page? How many physical memory accesses do you have? Yes. Siddhant says 2. This it is. First, we know that to access any address, any virtual address, it has to be mapped to a physical, the page map table. Page map table, because it resides in the memory, that means you are accessing one of the memory locations to obtain the frame number. Okay, so the first stage is logical address to page map. Page map table is in the physical memory, so that means you are accessing the physical memory once, and then once you get the frame number from that, then you perform another memory access to obtain that particular frame. So 2 memory accesses. Okay. Now, how do you distinguish that this portion is the page table and this portion is the rest of the process? How do you distinguish? We distinguish through dedicated registers. As you see here, there is a register called page table register or page table base register. What does it contain? It contains the base address of the block of code that contains the page table. I repeat, what does this register contain? The register contains the address or the base address of the block of memory which contains that page table. So in this case, if the page table is here and this is the address, this is your base address of the page table. Very similar to how we have base addresses of the different location of the different blocks of the pages or the segments. Similarly, we have the base address of the page table. This base address is what is present in or what we call the page table base register. Now, usually, in case of Intel 8086 processors, this is held in a register called CR3. It's very, very important. This is in CR3. Okay. What does the OS store? Where does this OS store? It stores this information that my page table starts from this address. This address means this physical memory address. But where does it store this? Well, it stores it in the process control block. So this information, the base address of the page table is stored in the process control block, because process control block is the portion of the process that contains every information about the process. So that is the reason why it's called the process control block. Now, each data and instruction requires two memory accesses. I've already told you that because the page table is also present in the memory, so obviously you'll have two accesses. This extra memory access is for the page table. Let me give you some problems that will highlight some problems so that we can motivate ourselves to more improved version of the paging scheme. So what is this page table issue? Let's quickly look at the example. Let us say we have a 32-bit address space. 32-bit address space means 4 GB of primary memory or physical memory. Let us assume that I have pages of size 4 KB, and let us say I have a page table of 4 bytes per entry. Okay. So what is the size of the page table? The size of the page table is, every page table is requiring, let's say 1, 2, 3, 4. So 4 bytes per entry. And from here to here, there are total 4K entries. Okay, 4K entries. So one page table, how many bytes is it holding? 4K entries, and each is having 4 bytes. So 16K bytes or 16 KB is the space that is occupied by one page table. One page table. We know that every process has a page table associated with that. So every process, in addition to its own space in the physical memory, will require an additional 16 KB of space for its page table. I repeat, for every process, in addition to its own space in the physical memory, will require an additional space of 16 KB for holding that page table. So if there are n number of processes, every process has requires 16 KB. So 16 n KB amount of space for n processes. So n process themselves will require some size. And in addition 16 NKB is additional space for holding the page table of each process. Look at this. So if this value of n is about, let's say, 16 KB. Suppose it is like you are running about 100 processes. So it's 1600 KB only for page table. Look, and that in this case, they are trying to find it's 4 KB and it's 4 bytes. And let us assume that you can at max go up to a situation where you are having 4 MB per process. 4 MB per process. So what he's trying to do here is, let us assume that this is the virtual address space. So 4 GB divided by 4 KB each page. So this is the number of pages you have. Multiplied by 4 bytes. This is the total amount of space for the page map table. And it comes out to be 4 MB. So 4 MB of the physical memory wasted in just for keeping page table of one process. Then if you have n processes, 4 MB into n. And if the n is large, you are running a lot of processes. See how much of a physical memory you are utilizing only for storing page tables. So what happens is, the address space are often sparse. What do you mean by that? We mean that few programs are using this 2 to the power 32 bytes. Very few programs. So can we just change this page table structure to save memory? This is the idea. Because ultimately we have to store it in the physical memory itself. Can you do some intelligent, some tricks to reduce or save memory? This is the idea that we do. So we call that hierarchical page table. What is this hierarchical page table? You break up the virtual address space into multiple page tables at different levels. For example, the one that you see here. So if this virtual address, let me show you the idea. This is the entire virtual address space from 0 to some max. You have divided into number of pages. And for the number of pages that you have, let's say there are n number of pages. Okay. For n number of pages, you have designed a page map table with n number of entries. And each one of them maps to a corresponding value in the physical memory. Okay. This maps to here, this maps to here, this maps to here. In this way, you mapped. But this is, if this is very large, this is creating a problem. So what we will do is, we will split this as well into a number of pages. The page map table is also split into number of pages. See, if this is your page map table, the page map table will have a certain number of entries. We just saw. What are the entries of that? It's equal to the number of pages, and each page will have a certain entry. If that is also very large, you split that up into number of pages of the page table. See, this is the page table. You have splitted the entire page table into number of blocks. And each block in this case is also a page table. That corresponds to a particular table. Look at this. So now you have two levels of page tables. One, which is holding the page entries of the virtual address space. And two, for every entry of this page table, there is a page table maintained. For every entry of this page table, there is a page table maintained, which is the second level of page table here. So this is the page table of the entries of the page table. So let me call them as an outer page table or page of the page table. Okay, so how is the addressing going to happen? The address will happen in this way. Previously, we were having a logical address and we were having an offset. This logical address took us to a page map table. This was the page map table. and this page map table would be so the logical address will take us to one of the entries of the page table. But remember that this, in the previous case, this would have directly took us to the content of this would directly take us to a primary memory or physical memory. But this time it is not the case because this is actually mapped to another page table. So this page map table now is also split up into number of pages. Okay, so that eventually will be taken to another page table, and the second level of page table will give you the frame number. So what we now have to do is we have to now split this portion into two components. The higher order bit will take me to the outer page table, and once I reach to the particular entry of the outer page table, I will read its components, and its component would take me to one of these pages. See, there are a number of pages here. This is page number 0, page number 1, page number 2, page number 3, and so on. So one of the component, this entry will take me to one of the component. Let's say this is entry number X. But how will I reach this entry number X? Well, this contains the offset. And what is this entry number X? So this entry, so no, this is not entry. This will take me to one of the page tables, okay, the corresponding page table. And then the next part of the logical address can be treated as an offset within that particular page table. Okay, so I will reach to that entry in the inner page table. And once I reach there, I will read the component or the entry of that particular location, and that will give me the frame number. That frame number added with the offset, which is here, would take me to the actual location. So I have two levels of paging. An outer page table, which again is divided into number of pages. So I will first have to find my entry in the outer page table, go there, read the component. That would take me to one of the inner page tables. I will reach to that inner page table, and then I'll obtain the corresponding entry for that inner page table. That will give me the frame number, add to the offset, and that will take me to the actual location. Just a typical example of the X86 page translation with 4 KB pages. You assume that we have 32-bit address space, and let us assume that 4 KB is the page. 4 KB page means 12 bits for page offset. This is 2 to the power 2 into 2 to the power 10. So 2 to the power 12. So because the page is 2 to the power 12 size, so to have one location within that page, you require log of 2 to the power 12. That means 12 bits for the page offset. Okay. So we are planning to find out. This is the 32-bit address space that is generated by the CPU. The CPU generates this logical address, which is of size 32. I just saw that it can be divided into P1, P2, and D, the outer page table, the inner page table, and the offset. We are trying to find out the sizes of each one of them, given that the page size is 4 KB. We identified that your offset will be of size 12. Now we are left with the rest of this, which is 20. How many bits of this higher order 20 will you allocate to for outer page table and for inner page table? That's the question. How many bits for the second level page table, that is for P2, and how many bits for P1? Let's begin with P2. Every page is of size 4 KB. So the question is, how many pages will I have? Okay, or how many? So if I divide this page into its number of pages, how many can I create? How many entries can I create? 4 KB is the size. 4 bytes is the entry of each. If I divide that, I have 1024 entries in my page table. 1024 entries means 10 bits to encode any one of those pages. 1024 means 2 to the power 10. So log of 2 to the power 10 is 10 bits for the second level page table. So this is 10 bits. So now if this is 10 bits, P1 is obviously 20 minus 10, which is 10 bits. So this is how we decide the number of bits for the first level, second level, and the offset. Start from the offset because that is fixed. Obtain that. Once you obtain, then you get the rest of the two higher order and the lower order page table sizes. And from the size of the page, you can calculate how much is required for the inner page table. Then automatically you'll get the outer page table. This is a very common question that is asked in examination as well as in interviews regarding the paging. So here you see a pictorial view of the paging architecture.
Sir, how did
Yes.
we said 4 bytes? 4 KB.
We are assuming that the entries of each page table is 4 bytes. Each page table entry is of size 4 bytes. So if the total page size is 4 KB and each entry is 4 bytes, how many entries you have? That's what we are calculating.
Okay, sir.
This is the pictorial view of how you see how the paging is done, the two-level paging. And as you see here, the outer page table is also called page directory. You see 31 to 22. This is used for the outer page level. And the base address of this page table is maintained in the CR3 register. We just discussed about that. Where do you start? So in this, how do you know that when you get an address, you have to look up to this particular page table. The page table resides in the physical memory itself. So you have to jump to that and check it. How do you know which portion of the physical memory should I jump so that I will get the page table? And you look up to the CR3 register, and the content of the CR3 register will take you to the page table directory. And then once the page table directory is obtained, then the architecture automatically will give you the page values, and then you can reach to the location in the physical memory. This is the CROTS 86 physical memory layout. Let's quickly have a look. What do we have? As you see in the diagram, it's from 0 to FF. This is the entire 4 GB space. Look at this, how the physical memory is divided. 4 GB of space has been divided into number of portions. Some portion is kept for BIOS. Some portion is kept for the different interfaces. Rest from 1 MB to 3 GB. This is for the user space, the accessible, which is accessible to the user. System BIOS, extended BIOS, video card memories used for the graphics and all. And again, this is for the accessible memory, which is anyone can use that. So now this is typical of Cross 86, that is Intel processors. It may vary from processor to processor. Okay, so what exactly are we doing? Left hand side is the processes, the physical memory. Right hand side is the virtual address space. And as you see, each one of them has to be mapped to this entire 4 GB space of the physical memory. We have some part as the kernel space, some part as the stack, This is the memory mapping segment, the heap, the BSS segment. This is the segment that contains static variables, filled with zeros, etc. The data segment and the text segment. So all of this. This is again taking 3 GB of space, and 1 GB is reserved for the kernel. Look how the mapping will happen. Okay, that's not. This is a view of the Xv6 address space. It's again very similar as you see. On the left hand side is the virtual address space. The portion which is highlighted in blue, within that you have the free memory, which is to be used by the users in the user space. And so this is the free memory which is in the kernel, and the one which is shown in the green is the one which is used by the user. Okay, you'll come across all this in the lab. This is to show you the files that are used for Xv6. Now, so what was the idea that we have seen so far? That you have a page table and the page table resides inside the physical memory. Now, the problem is that page table has to be accessed in order to access any particular frame, okay, or any page in the physical memory. The question is, because we are having 2 memory accesses, now if you keep on increasing the size of the page table, or if you increase the hierarchy of the page table, previously one page table was in one physical memory. If you split that into 2, outer and inner, both of them will be in the same physical memory. So the moment you keep on increasing the hierarchy, you are actually keeping them in the same memory. And the problem is that the access time will increase, because every time you have to search in that particular physical memory and obtain that location. Can we make this thing faster? We can. And for that, we are going to use a cache. I hope all of you remember the concept of cache. What is cache? It's a fast memory which is usually kept between the CPU and the primary memory. And what does it contain? It contains only the relevant portions of the program which is frequently accessed. Why? Because when we run a program, we don't run a program all at once. We are only working on a very small portion of the program. And there is a very interesting feature in a program which is called locality of reference. That is, if you are currently executing some instruction now, there is high probability that you will either execute the same instruction again, or you will execute instructions which are closer to that instruction in the memory. So this is called spatial locality and temporal locality. Just see. Temporal means you access the locations which have been accessed just now. Very common is the for loop, the looping constructs that we have. When you loop, you know that these are the instructions which will be again executed. For, let's say, the number of iterations is some n. So n minus 1 times, you will execute the same instruction every time with a different data, obviously. And spatial locality is, if you are executing some instruction now, there is high probability that its nearest instruction will be executed. Nearest means the one which is adjacent in the memory. So if this is the case, why don't we make use of that? Of what? Of the page tables. So if you are executing a program that is currently executing page table or page table entry 0, there is high probability that page table entry 1 will be executed next, then 2. So instead of keeping the entire page, find out which are the pages which are frequently accessed. So if you have a page table entry or page table which is very large, you don't need to keep the entire page. Just find out of that entire page table, which are the pages that are very frequently used. Let's keep only those entries of the page table. Let's say this page table contains, say, 0 to some 99, 100 entries. But I find that this 0, the 5th one, the 55th one, these are the ones which are very common. So can I create a very small memory and I can create only these three, 0, 5, and 55, only the entries of this. And this is a very fast memory. This is a cache memory. And when I will be looking up to, when I need to look up to the page table, I will first look up to this page table, which is the faster page table. And then if I don't get it here, then I can come back. Very similar to the cache concept. And this cache that you create is called TLB. And it is called Translation Look Aside Buffer. And it is an associative memory. Associative memory, what is the idea of associative cache? It's a memory in which all the items or all the locations are compared at the same time, that is parallel. So if there is a particular logical address that is generated, the page value is calculated from this logical address, and that is used to compare with all of them at the same time. So let's say you split this up into P and D, you obtain this P and you compare it with all the entries of this faster page table at the same time. If it is there, you claim, oh, it is there, get that value, get the frame number, and you are done. So very similar to the cache hit. But if it is not here, the page that you're looking for is not in this cache, then you have to go back to this bigger page table and search it from here. This is the concept of TLPs. It's a fast lookup hardware cache. Look at this. The CPU has generated a logical address. The page table has been identified. The page number has been read, and the page number is searched in this entire TLB. Once that any one of them is a hit, this is called TLB hit, that this page number that you are looking for is indeed in this TLB. You have a cache hit. So if you have a cache hit, automatically its frame number is read and the offset is added and you are done. The problem is if there is no TLB hit, then what happens? Then no problem, you proceed that to the actual page table. The page value, the page number is obtained, frame is read, added to the offset, and then you reach to the physical memory. So this is what happens if you are handling paging hardware with TLB. It's a very, very important concept, and TLB is the one that is most vulnerable. I'll talk about that when I come to security. Majority of the attacks that happen today on different systems is through this TLB. This is the area where people try to attack, because if you are able to change the permission of a particular page, it is here that you have to make the change. Remember, what do we have as the content of page table? Some entries along with protection bits. Suppose there's a protection bit which says you are not allowed to access that, you're not allowed to write. But if you can get hold of this and change it, then you are able to access the page. This is one of the vulnerable areas which people target. We'll talk about buffer overflow attacks, which actually happens to this particular TLB. The TLBs are the ones that are attacked to obtain information. Okay, so effective access time with TLB. I am not going into the details of that. It will be there. It is just very similar to the calculation that we have in a general cache. That if you are searching for a TLB, because it's an associative cache, you have to find out what is the hit time. If you don't have a hit, then you add that additional searching time along with the miss time, and that is what we call the penalty. So depending on the architecture, the TLB misses are handled in either hardware or software. If it is a hardware, then it's a very complex thing. And as a software, then you have to find out what is the problem. and fix that. Okay. What happens to TLB on context switches? Well, one is you flush the entire TLB. Context switch means you move from one program to the other. So when you are moving from one program to the other, the page table which was there, the TLB which was maintained, which contain entries of the page table of process 1, now has to be overwritten by the page table of the second process. So what you do is, first option is you flush the entire TLB. You load the CR3 with a new value. Okay, that's the first thing. Second is you attach the process ID to the TLB entries so that you can understand that, okay, which is the process that is going on, whose contents are currently present in the TLB. This is what MIPS and Spark processors do. There are different ways to handle this. So let me quickly complete this discussion with some of the different styles of paging that people have proposed. We have already seen something called copy on write. If you remember, how many of you remember copy on write? Okay, if you don't, I'll just recapitulate. It was a concept where the parent and the child processes, as you see here, they share the same pages. Remember when I said you have a process P1 and process P1 forks, what happens? P1 gives rise to its child, which is an identical copy of P1. So the address space of P1 will have an exact copy of the address space. When I say address space, I'm meaning virtual address space. So virtual address space is 2 copies, understood. But does it mean that I would like to have the same one more copy in the physical address space? If this virtual address space is divided into 3 pages, and these 3 pages are here, should I have one more copy of these 3 pages for the child of P1? Does it really make any sense? Do you understand what I'm saying? P1 and its child both are having their respective virtual address space, and both can be split up into page number 0, page number 1, page number 2. See, for the process P1, this is page number 0, page number 1, page number 2. Tell me, should I also have the same 3 pages again for page number 0, page number 1? Does it really necessary? No.
No, sir.
Because content wise, they are the same thing. Why should I have physically again an additional copy of the same content? I just have to have a proper mapping that this will also be mapped to this, this will also be mapped to this. This is all I want. So that is what it says, the copy on write. That is, parent and child, they share the same pages. Only you make changes if you have written to a particular page. If this P1, the parent writes to this and P1 child doesn't want to write. If that is the case, then maybe you need 2 copies, one for the child, one for the parent. Then the parent makes changes here and the child makes changes to this. So as long as they don't make changes or they don't perform a write operation, you don't need to have 2 separate copies. Keep a separate copy of the page, only that page, if both processes are making changes differently to that particular page. This has been shown here. As you see, pages are being shared. So process P1 and P2, both are sharing ED1, ED2, ED3. Again, 346, 346, the frame numbers. This is also having 346. This is also having 346. And both of them are having 346, which contains 3, 4, and 6. The ED1 is shared. Differences in this page. This is page number 0, page number 1, 2, 3. Page number 0, 1, 2, 3. Page number 012 is same for both processes. So they are sharing the same space or same frame in the physical memory. Difference is in their data. That is page number 3. So page number 3 will be different. And that will be different from data 1 and data 3. Okay. And similarly for data 2 as well. So these are the pages which are. Okay. I'll not go into this because it's already covered, or maybe we know that that's a typical example of how segments are selected in case of 8086 processors. They have separate registers that contain address of the different segments, code, stack, data. They are given the names in this way. So 8086 actually keeps separate registers so that they can hold the base address of each segment. This is how Intel started off. This is an example of how Linux allows or uses 3-level paging. We said paging can be 2-level, but it's not only 2-level, you can extend the level to many. And as you see here, it's a 3-level paging, where even the outer page can be again split up into 2 pages. So outer page will lead to an inner page. The inner page, again, each inner page can be again split up into a number of pages. And for every entry, there can be a page. This is how Linux supports 3-level paging. So in that case, you'll have your address, logical address, split it up into P1, P2, P3, and then D. So this is the entire logical address space. So this is the offset. This entire thing is your logical address. You can go at max up to 7 levels of paging. 7 levels. Linux supports 3. Okay. We also have a few different kind of page table structures which people have proposed. Hierarchical paging we have already seen. The second category of page is called a hashed page. You know the hashing function. What is that? Now the page table, instead of containing a simple frame, it actually contains a chain of elements. Let me show you what. This is what is the idea. It's called hashed page table. Now what this hash is, you have the logical address which gives you the page number. But the page number is obtained and there's a function that operates on this page. And it is not a simple page table. You call it a hash page table because when you apply the hashing function on the page number, that takes you to an entry, and this entry is a linked list. What do you have in this linked list? Well, you have list of elements. So the list of elements that you reach to will be obtained in this way. Let's say the hashing function that you have is some value that you obtain here. You scan the list. Which hashing function have you got? Is it Q? No, it's not Q. If it is not Q, well, you move ahead. You go to the next element in the list. Is it P? Yes, it is P. If it is P, then the next entry in this particular element of the list is the frame. So the hashing function will take you to an entry in the table, and now the entry of each of that table will be a list. You start scanning the list. Each entry in that list will be the page number that you are searching for. See, this is a list it is maintained. You started off with P. Start scanning. Look at this. It is not P. I move to the next location. P, yes, it matches to this. So that means the next value, the second element in this is my frame. It is R. So what do? Well, you save this, right? Instead of having a table, you have a linked list. That's the difference. It's called a hash page table. The other way could be something called inverted page table. It's just the opposite of how the paging works. Page table works in this way. For every page, you maintain a frame, right? For every page will take you to a frame. How about the other way around? That is one entry for each real page. Now the page table that I will maintain, usually what do? The page table entries are decided, or the number of pages are decided by the virtual address space. The virtual address space is split up into number of pages and those many entries I have. Can it be the other way around? That is, now my page table will be based on the number of frames that I have, not on the number of pages, but number of frames. That's the difference. So I'm not bothered about how many pages you have created for this virtual address space. You may create maybe 3, but I have used 1, 2, 3, 4, 5, 6, depending on how many frames I have created. 1, 2, 3, 4, 5, 6. This is my physical memory. So my number of entries in my page table will be decided by this. Okay. And what is the idea behind this? The idea is this, that for every entry, you will have its corresponding frame, which is already there. Okay, let's understand this. The CPU will generate a logical address. The logical address that you generate will contain P and D. But the problem is you are not getting the value of this P to search in this table. Okay. So what exactly are you going to, or how will this happen? Well, interesting thing is, because you are now containing a table that contains not with respect to the pages, but with respect to the frames. The problem is that if you are maintaining the frame information, the frames can be of different processes. Suppose this is frame number 0, frame number 1, frame number 2, frame number 3, frame number 4, frame number 5. Good. What does frame number 0 contain? It contains the first page of process 1. Let's name it in this way. What does frame number 1 contain? It contains page number 2 of process 1. Okay. What does frame number 2 contain? It contains page number 2 of process 3. See? So if you maintain this information, that if you can load the content of this here, if you load the content of this here, if you load the content of this here, your table, which you call page table or whatever name you give, it does not contain pages of only one process. It contains pages of many processes. So when some process is working and CPU is generating some address and wants to access any address of this process, looking up to this particular page will be confusing. Okay, how will I know which page of process P1 is currently accessed? Because this table can contain pages of other processes as well. So to avoid that, I would be attaching the PID with the address. PID is process ID. And what will the table contain? Very similar to the usual page table. What does a page table contain? The page table contains the frame number. But this page table will contain page number. Interesting. Because this page table, or this, whatever you give the name, inverted page table, it is mapped to a frame, not to a page. So the entry of this table will be a page and not a frame. This is the usual page table. This is the inverted page table. But it is not enough to contain the page information. You must also associate a PID. Because if you don't attach this, you will not know whose page, which page of which process is in this particular entry. So now let's understand. The table contains number of entries corresponding to number of frames of the physical memory. If there are number of frames, suppose 1024 frames have been created in physical memory, this table will contain 1024 entries. Each entry will correspond to the frame of this. But the frames of the physical memory can contain pages of different processes. So I will also maintain PID and the page of that particular process. When the CPU will generate the address, the first thing that I will do is I will compare the PID with all the PIDs of all entries of the page table. The entry which matches, that means that entry contains a page of this particular process. So I will first compare by matching the PIDs. Once the PIDs get matched, then I will read the value of P. But the value of P will be the same as this. All I need to know is, because I have just mapped a frame to this particular table, there is no mapping as such I require. All require is the offset. Why? Because I have the first frame here is put in the first entry of this. Second one is here. Third one is here. So if I just find out which entry matched with my PID, I will count its offset from the top, and that same amount of entry I will read from the top of the physical memory, and I will get to that particular page. That's it. This is what I do. Get the address, match the PID, the entry in the table that matches, read, see from where is it lying from the top, the same amount you read from the physical memory, the value of the page that you reach to is your relevant page. The next, read the offset, and the same offset within that particular page is the address that you are looking for. This is called inverted page table. Is this clear to everyone? This is another way of handling the paging concept. Okay. So this is all about the mechanism of performing memory management. This is how the operating system performs memory management. Okay. Okay, so in the discussion so far, we saw how by using different kind of schemes, we are able to manage the memory. Now, there is one more problem that needs to be resolved, or we can say we can think about a better solution to this. And the problem is that what happens if you look at the way in which the code works. Okay, so let me give you the idea of the problem. The problem is that virtual memory is larger than the physical memory. Okay, let me try to elaborate the problem. Here is a process P1. The process has its own virtual address space from some 0 to some, let's say, m-1, some m size. P2 is also some 0 to m-1. Then we have P3, P4 in this way. But the physical memory, okay, is only of size 0 to m-1. That is only size m. Now see the situation. You have different processes. All of them are of size m. You have to fit all of them into the physical memory. But the physical memory is only of size m, or maybe of size n, let us say. And n is less than even m. Now what to do? You get the problem? The virtual memory is much larger than the physical memory. One program itself, the amount of space that that particular program or process would occupy is more than the space given to the physical memory, more than the physical memory space available. Add to that, you want to keep 2 to 3 processes at the same time. Now see the problem. Which means if the virtual memory is larger than the physical memory, which means that the number of pages is larger than the number of available frames. That's the problem. Okay, if I'm talking about the paging scheme, this is the situation that we have. So what to do? How to handle this problem? The easiest solution is that do I really need to keep all the pages of this virtual address? Do I need to keep all the pages of process P1? So when I am working with process P1, I see that there are, let's say, some 4 to 5 pages of P1. When you are working with process P1, are you requiring all the 5 pages? This is the question. Do you really require all the 5 pages when you are working with P1? The answer is no. Why? Because when you are working with P1, when this process P1 is executed by the CPU, you don't work with all instructions at the same time. You first execute instructions of page 0, then you move to executing instructions of page 1, then you complete instructions of page 2. This is how you do. You first complete instructions of page 0, then page 1, then page 2. Which means you are not working with all the pages of process P1 at the same time. Nobody works. So when you are executing a process PI, all pages of process PI are not executed or not required at the same time. You are executing with only one page maybe, or maybe 2 pages. So if process P1 requires M pages or has M pages, in the physical memory, I do not need to keep all the pages. I will only keep page 0 of process 1 and maybe page 1 of process 1. That is all. But you may ask, sir, but later on, I will need process 2. Yes, I will need. But when I need process 2, I don't need process 0. So then I will override this with process 2 of page 2 of process 1. So see, I am not requiring all the pages, and how by intelligently removing one page and filling that space by another page of the same process, I am ensuring that at a time I will require only 2 pages of process 1 to be there. Good. What do you achieve? Well, I achieve a lot of space. Now that I am only keeping 2 pages of process P1 at a point, the other space of the physical memory can be utilized for keeping pages of other process. Say, for example, I will keep page 2. This is say page 1 of process 2, page 0 of process 2. For that also I can use the same principle. For process 2 also, I don't need all pages at the same time. I will only keep pages which are currently executed when the process P2 is running. Okay. And this is called demand paging. What is demand paging? You bring the page only when it is needed. Then where does these pages reside? Where do they reside? Well, they reside in the secondary storage device. They are residing in the secondary storage device. Only when they are required, they are brought into the physical memory. Until they are required, they will not be brought. Only the pages that currently are required are brought in. This is why the name demand paging. When you demand a page, you bring it. When its task is over, you send it back, so that you do not unnecessarily occupy space when it is not needed. This is the concept of demand paging. Okay. So what is the basic idea? Let me show you. Yes. Now, I can bring the entire process into the memory at load time. This is one option, but it is not needed. Why? Because not all pages are executed simultaneously. So what you do is you bring one page into the memory only when it is needed. This is the basic principle of demand paging. Why? Less I/O is needed, no unnecessary I/O, less memory needed, yes, because you are only consuming 2 pages in the physical memory for a particular process, 2, 3, depending on how many you are keeping at a particular point of time. For example, process or program A is bringing in 1, 2, 3, 4. That is page number 4, 5, 6, and 7. It has moved out and it has brought in 17, 18, 19, 20. It has brought in 3 pages. It has brought in 3 pages of program B and moved out 4 pages of program A. So constantly pages will move from the hard disk to the primary memory, from primary memory to the hard disk. Interestingly, this hard disk now, it acts like a memory. This hard disk, it is acting as an extended memory. See, you are utilizing the hard disk as a memory where you are keeping the pages. So there is a specific portion in the hard disk where all this paging, all those pages are kept, and that is called a swap space, the swap. I hope many of you have done that if you have installed Linux. When you install Linux, Ubuntu, it asks you what is the amount of swap space you want to keep. Have you seen that? This is the hard disk space that is utilized for keeping those pages. Which pages? Pages which will be moved in and out into the physical memory. Why are we doing this? To save space, faster response, more users. Yes, more users means more processes can be accommodated. It is similar to paging scheme, except that it is a demand paging. What is this? The page is needed, a reference to that. Here is the interesting thing. Now the idea is, let me show you the algorithm that will clear the picture. Okay, suppose a process P1 is currently executed. Process P1 requires, to completely execute process P1, you require 4 pages. Okay, page number 0, 1, 2, 3. There is another process P2 which requires 3 pages, 0, 1, 2. I have a physical memory that contains only 3 frames. Frame number 0, frame number 1, frame number 2. The question is, who will reside in these 3 frames? Well, I say page number 0 of process number 1, page number 1 of process number 1, page number 0 of process number 2. This is how I have placed those pages. Is it work? Does it work? Yes, it works. Why? Because I'm not working with all pages of P1 or P2 at the same time. So this is the situation I have. Now, there is an address which is generated for some location of page number 1 of process number 1. Okay, no problem. The memory management unit takes care of that. This is provided to the memory management unit. The memory management unit, which is a paging scheme, gives me the equivalent frame number. I reach to that particular frame and I obtain the address. Good enough. Next time, there is an address which is generated for page number 2 of process number 1. Page number 2 of process number 1. Okay. Page number 2 of process number 1, I look up to the page table. I look up to the page table of process P1 and I find that for address page number 2, there is no valid entry. This bit is a 0 here. There is no valid entry. The moment I get an invalid entry, I declare that this page does not reside in the physical memory. This page does not reside in the physical memory. And this situation where that particular page does not reside in the physical memory is called a page fault. Okay, it's a page fault. What happens? The page that you are looking for is not in the physical memory. How did you find that out? Well, I checked that valid bit and I found that the valid bit is not there. So when I translate that MMU, we just saw when the translation was done for that particular page of process number 1, I found that it was an invalid bit and it gave me an invalid bit mentioning or declaring that the page does not exist. And this condition is called a page fault. Well, what happens if you have a page fault? This is the situation that you have. Let's look at this. This is the logical memory. And here you have the current situation. We have A, B, C, D, and this is the number of pages that you have. This is the frame. Okay, this is the frame number. So what you see is this is the page table content. Look at the page table content. You have the frame number 4, frame number 6, and frame number 9. This is in page map to page number 0, page number 0, page number 2, and page number 5. A, C, and F. A, C, and F. A is frame number 4. C is frame number 6. F is frame number 9. I have placed them in the corresponding page table, corresponding page entries. Good enough. How about D, E, G, H? What will I get for them? I will get invalid bits because they do not reside in the page table. They do not reside in the page table. So suppose there is an address that wants to fetch this page, okay, page number 4. When it wants to fetch page number 4, that page entry will be looked up in the page table and will find that its page table here is showing I, which means it's an invalid bit. That is, the page is currently not in the physical memory. Yes, it is not in the physical memory. And this means a page fault. The moment it declares a page fault, we know that the page is not in the physical memory. It has to be brought in the physical memory. So what will happen is this particular page, the E, this will be brought into the physical memory. And if there is a free frame where it can sit, yes, there are free frames here, it will be placed. And its corresponding entry 1 will now be, the first thing it will do is this will be updated to V. This value will be dropped here, and now we have a valid page. Let's summarize. Virtual address was generated, page was identified, page table was consulted. It was found that the valid bit, there's an invalid bit. It meant that that corresponding page does not exist in the physical memory. This situation is called a page fault. If there is a page fault, the page which is residing in the hard disk is brought into the physical memory. It is placed in the physical memory provided there is a space for placing that. If it is placed, the corresponding frame number is updated in the page table and the invalid bit is changed into a valid bit. Now the page is there. Next time when the address will be sent, it will find that yes, there is a valid bit. This is the concept of paging, demand paging. Is the concept clear? It's a pretty simple thing, just very, very logical. Think for yourself when you get the answer. Okay. So the overall summary is, if there is a reference to a page, the page and the first reference to the page will trap to the operating system. That means it will generate an interrupt or a trap mentioning that the page is not there. So see, you applied this logical address to the memory management unit. The memory management unit looked up to the page table, found that the valid bit is it's invalid. Immediately when the bit becomes invalid, it sends an information through an interrupt to the operating system. There's a page fault. So the memory management unit now understands that there's a page fault. Now we have to jump to a different location, bring that page. So operating system looks at another table to decide the invalid reference, not just in memory. Find the free frame, find whether there is a free frame, swap the page into the frame, reset the table to indicate that the memory is now having the page, and set the valid bit to V, and restart the instruction that caused the page fault. The instruction that was required by the CPU ended up into a page fault. And until the page was brought into the memory, the instruction was kept on hold. When the page is now brought into the memory, the instruction is restart. This is the mechanism of handling page faults. That's the pictorial view, as you see here. There's a reference, which is 1. Page table is looked up. Page table finds an invalid page, sends a trap to the operating system. The operating system stops the entire operation, sends to the backup store, which is the hard disk. This is stage number 3. The page is put into the free frame. This is stage number 4. And once the frame is now available in the memory, the page table has to be updated. And you restart the instruction. So this is how you handle page faults. Okay. What are the aspects of demand paging? You start the process when you initiate everything, just you are starting your system. Obviously, there is no page. When you just started, remember when you just start your system and when the process begins, obviously there is no page of that particular process. Okay. So there is no pages in the memory. This is where you start with. So remember, every process starts with the page fault. Because whenever the first instruction is sent, there are currently no pages in the memory. So the first instruction itself will say that I have a page fault because there are no pages. So the first page is brought in. When the first page is brought in, then the next instruction is sent. If you are going to the next page, that will again have a page fault. So the first few instructions will have, no, first I wouldn't say first few instructions. When the first instruction comes, the entire page comes. So maybe the next instruction will be in the same page, no problem. But after some instruction, when you go to the next page, you will again have a page fault. Again, that same second page has to be brought in. After some more instruction, you will again have a page fault because page 3 is not there. So this is the idea. The OS, what it does is it sets the instruction pointer to the first instruction of the process. First instruction. Automatically, the first instruction is in page 1 and page 1 is not there. So you have a page fault. And for every other process pages on first axis. Remember, the entire system works on demand paging. You do not load pages immediately when you start the process. No. Pages get loaded one by one, and they are done through demand paging. So the moment you start your system or you start any process, there is a page fault. Okay. Actually, a given instruction could access multiple pages. Multiple page fault. Yes, that can happen. Maybe one instruction which the CPU has sent first requires page 1 fault, page 1 is brought. But the instruction also requires page 2. It's also not there, page fault, bring page 2. To complete the instruction, it also requires page 3. It is also not there, bring page 3. So in this way, our instruction can require multiple pages and you can have series of page faults. Okay. Consider the fetch and decode of an instruction which adds 2 numbers from memory. Yes, because the 2 numbers can be on 2 different pages and both pages are not there. So you'll have a fault. So what we actually have is you need to have some hardware support to handle demand paging. And we need page table with the valid invalid bit. We need secondary memory, a swap device with swap space that will hold those pages, and the instruction restart. So that is a pictorial view of the problem. I'll not go much deeper into that. Please go through this. It is just a pictorial view of how the entire demand paging works. It's the worst case. Okay. Now, what we have not mentioned is there are a lot of internal operations which are taking place, like saving the state, etc. Because whenever you have an interrupt, you have to save state. This is what has been mentioned here. I'm not detailing that out. Okay. So the performance of this demand paging is basically dependent on 3 major activities. Number 1, service the interrupt. Yes, because whenever there's a page fault, there's a trap that is sent to the operating system. Trap means an interrupt. Interrupt means whatever was going on has to be saved. That's the first thing to do. Then you read the page, which also takes a lot of time. And finally, the process which was put to hold because the page was being fixed has to be restarted, which is a small amount of time. So the majority of the time that you spend is in reading the page. Look at this. So the page fault rate, how frequently you get page faults. If you say P equal to 0, let's call P is the rate. No page fault. And 1 means every reference is a page fault. It's like the minimum probability and the maximum probability. When you have minimum probability is 0 and maximum probability is 1, so you have a lot of page faults. So what is the effective time that you spend in handling page fault? It's like 1 minus P times memory access. 1 minus P is the rate of page fault. And if you have a page fault, P, then you will have some overhead. What is this overhead? Page fault, swapping out a page, bringing in a page. So this additional time that you spend is the effective access time. This is the our numerical value, example showing what is the typical value that you have if you have page faults. If your memory access time is 200 nanosecond and every page fault service requires 8 millisecond, what you finally have is effective time is 8.2 microsecond, which is slowdown factor of 40. So you are running your program at a particular rate and you are slowing down the entire process by a factor of 40. Why? Because remember, you are bringing the pages from the hard disk, which is a slow device. So what happens is, and interestingly, you are getting one page fault in every 400,000 memory accesses. Every time you're trying to access something, you're getting one page fault. So this is the basic problem of demand paging, and it can be optimized. It has been optimized. There are a number of ways in which people have optimized that, increasing the swap space, allowing, as you see, yeah, that's one of the basic, very common one, increasing the swap space and all. We've already discussed this. So there are a number of algorithms which, this is the problem, and I'll finish off with this. What happens if there is no free frame? You are bringing a page and you want it to be placed in the physical memory, but there is no space for physical memory to keep that page. What do? What should be done? Suppose there are people who want to listen to my lecture who are standing outside my classroom, and there are some people who are sleeping inside my classroom. So I would remove those people who are sleeping. In any case, they are doing nothing, and allow, yes, and I allow some pages to be taken in. That is exactly the idea. So the algorithm is, you have to swap out some page and you replace some page. Which pages are you going to replace? The pages that are going to be replaced will be decided by some algorithm. Okay. And the page replacement, as you see, is prevent over allocation of memory by modifying page fault service routine to include page replacement. Ensure page replacement, number one. Okay. And second is, use a special bit called dirty bit to reduce overhead of page transfers. I'll show you what. Keep this in mind and look at the algorithm. Here you go. Suppose I have to load this particular page number 1. Page number 1 does not exist here. So I will get an invalid page. The moment I will get an invalid page, I have to go to the hard disk and bring this. So I have to bring this M and load it somewhere here in frame number 4 and update page number 1 with entry of 4. This is what I have to do. Okay, the problem is if I don't have enough space. This is what I was. So you find the location of the desired page, find a free frame. If there is a free frame, use it. But if there is no free frame, use a page replacement algorithm to select a victim frame. Now, who will be this victim frame? That has to be decided. That is decided through number of algorithms. And I'm going to talk about some of the algorithm. We are not going to go into details. It's pretty simple algorithm. You just have to look up to this, and I'll talk about one of the problems and we'll finish on this. So there are a lot of examples that have been cited. The 3 different algorithms. The idea is that try to find out which page should be removed. If you look at the trend, you see that as the number of frames, let me give you an example. Let's say this is the reference string. Reference string is the number of the virtual addresses that are being the virtual addresses which are generated. Okay, and if this virtual addresses correspond to a particular frame, now this diagram clearly shows that as the number of frames increase, the number of page fault decreases. What I mean is, let's see. Suppose I have this is the reference string, and I just have 3 frames. Okay, this is the string that I have, which is the page numbers. These are the page numbers, and I just have 3 frames. Okay, let me give an example. Suppose I decide to allocate or use demand paging scheme. First page 7, is it there in the frame? No, I will put it. So first I will have a page fault. Okay, page fault, I will bring the page, keep it in one of the frame. Done. Next, is 0 in the frame? No, again a page fault. Again I will bring 0. Done. 1, is it in this? No, again a page fault. I will bring 1. Done. 2, is 2 here? No, I have to, is there space? No, I have to replace one of them. Let's go with this approach. Least or first in first, the one which came first will be sent out first. I update 7 with 2. So I remove page number 7 from the physical memory. I replace that with page number 2. Remember, I already have got 1, 2, 3, 4 page faults have become. 0 is there, so I have a hit. 3 is not there. Which will I remove? Okay, I will remove this and replace it with 3. There was a page fault here, and I this. 0 is already there. Hit. 4, no, 4 is not there. Let me remove 2 by 4. I just remove 2 by 4 and immediately I have 2. See, look at the problem. I just remove 4, I just remove 2, and immediately the next reference was again 2. This is the problem. If you could just analyze the string and would have allocated them, you would not have this problem. Had you an idea of what is going to come next, you would never have removed 2, or you would not have updated 2 with 4 if you would have looked at what 2 is going to come. But the problem is I don't know that 2 is going to come. I cannot see the future. I cannot know which page is going to come. The other thing that I could have done is, if I had, instead of 3, 4 frames, then even if 2 was there, I could have placed 4 in this free space. Because I do not have enough free frames, that is the problem. And if I would have 4 frames instead of 3, this page fault would have been avoided. This is what is mentioned in this diagram. That if you increase the number of frames, your page fault decreases. See, if you have lower number of frames available, you have a very high page fault. If the number of frames keep on increasing, your page fault keeps decreasing. This is what this particular diagram or the graph shows. Now, in the previous example that I have shown, this allocation, I will come to that. So this is the allocation that I was referring to. And the algorithm that we are using is called first in, first out algorithm. This is the reference string which refers to the page numbers. We have 3 frames, and this reference string, the pages have to be allocated to the frames. We start with an absolutely blank physical memory. So initially we have a fault, and you are measuring how many faults you are getting finally to allocate each one of them. You see that you have 15 faults. And by the rule, we know that if we could have more number of frames, we could have reduced that. We could have reduced the number of faults. But interestingly, this algorithm also has an anomaly, or we call Ballard's anomaly, where in some cases you see reducing the number of or increasing the number of frames actually creates more number of page faults. It is given in your book. Please refer to that. You will see that there is an example where given a string and 3 frames, when you increase it to 4, you will actually find that the number of page faults will increase. So that's kind of an anomaly. Should not have, but it happens. Isn't it? So this is the algorithm that I wanted to mention. This is a diagram that shows Ballard's anomaly, that some point of time the number of page faults reduces, but going beyond the number of frames, it again starts increasing. That's the point which shows Ballard's anomaly. There are 2 other algorithms that handles that. One is called the least recently used and optimal. Optimal is when you know what is going to come next, and accordingly you allocate. But that's not possible because you don't know the future. You don't know which processes are going to come, which pages are going to come. So finally, we end up into something called least recently used. We decide on which page to be removed based on which was recently used. Least recently used. So you look at the past knowledge rather than the future. Optimal says that you should go into the future to see. That's not feasible. So you replace the page that has not been used for the most amount of time and associate a time of last usage. For example, in this, find out which is the page which was last used, that it did not figure in this reference. If some page has to be replaced, that is the one that should be done. You may wonder, how is it maintained? Well, you maintain a timestamp. And every time there's a page replacement that has to be done, you look at the timestamp. The minimum is the one that is least recently used, replace it. So I'm going to stop it here. There's one more concept that I would have liked to discuss. It's called thrashing, but not today. So with this, we cover the memory management unit of this course.